Today we're going to take a look at differentiation and integration on these vector valued functions. So we're going to start with the definition. And this definition will bring back fond memories. The derivative of a vector valued function R of t is r prime of t, which equals the limit as delta t goes to 0 of r of t plus delta t minus r of t over delta t for all t for which the limit exists. If r prime of t exists, then r is differentiable. At t. And then if r prime of t exists for all t in our interval, then r is differentiable on I. Okay, like that should trigger some thoughts anyway, right? Things you've seen before, limit definition of derivatives, all that stuff. We're not going to use the limit definition to find our derivatives, but the process is the same, just the same. So we're going to look at a theorem next. Theorem 12.1 says the following. If r of t is f of t I plus g of t j plus h of t k, where f, g, and h are differentiable functions of t, then r of t equals f prime of t I plus g prime of t j plus h prime of t k. And that's coming from what we did in the last section with limits, right? Derivatives are limits of a specific variety. We already learned that we can move the limit through each of these vector valued functions to each of the individual functions of the components, and we can do them from that perspective. So let's do an example. So we're going to find the derivative of r of t, which equals the vector. We're going to write it in the component form like this instead of ijk for this one. All right, so we have e to the t squared t squared e to the 2t, and then secant of 2t. And I'm going to give us a little bit more space here. All right, so what's the derivative of e to the t squared? Monica said 2t. That's part of it. What's next? 2t e to the t squared. Our j component, t squared e to the 2t.
Two t e to the 2t plus 2t squared e to the 2t.
And that's it. Are you good with that one? How about secant of 2t? That's part of it. Ah, we're missing a 2. Why are we missing that 2, Ashlyn?
Because you have to drive the inside.
Right, the derivative of the 2t gives us a 2 on the outside as well. Yep. All right, straightforward enough? Okay, so brush up on the derivative facts. We did it at the beginning of the semester. We've taken a little bit of a break. Haven't done many of them since then, but yes. Okay, so the next one that we're going to do is a multi-part problem. It's going to have a lot of components. So we're going to find several things. A, we're going to find is r prime of t. For B, we're going to find r double prime of t. For C, we're going to find r prime of t, the dot product of r double prime of t. How much space do I have? I still have enough. Okay, D is the same thing with the cross product of r prime of t and r double prime of t. And we're going to do all of this for the function r of t equals 1/2 t squared I minus t j plus 1/6 t cubed k. Okay, so take a minute, at least do the first two parts. R prime of t, r double prime of t. We'll just check in real quick and make sure we have the same components. And then we'll do the dot product and the cross product. So pause after you've got A, B, and let me kind of just give me some eye contact so I know where we are. Okay, what did we get for r prime of t? Ti. Keep going.
Minus j
Mm-hmm.
plus 1/2 t squared k.
Okay, does everybody have that? Fabulous. How about for r double prime of t?
Minus tk.
I and then
Okay.
plus tk, right? Okay.
Yeah.
So, okay, just making sure. I plus tk. Good. So we have a 0 in the middle there. If you want to write the 0 in for the purposes of the next part, you certainly could. So we need the dot product. What do we do for dot product? you multiply the coefficients of the components, or the vector pieces of the components, not the ijk's, but the other pieces, right? So we have r prime of t dot r double prime of t. So on the first one, it would be t times what? 1. And then I would have technically plus a -1 times 0. And then I would have a 1/2 t squared times
Or
t. Yep. If we simplify, what do we have? T plus 1/2 t to the third. Okay, so when we're working with functions, we're not necessarily going to get coefficients. That should make sense to us. And then the last one, part D, is the cross product. So r prime of t cross r double prime of t. And we will do our expansion of our determinant. So in the first one, I have -1, and I have 1/2 t squared. And then I have 0 and t, I. So remember, that's the jk components of the second, or the j and k components of our vectors, times I. And then we have subtraction. I have t, and I have 1/2 t squared, the I and k components, 1 and t. This one's times j. And then I have t and 1, -1 and 0. So the ij components times k. All right, take a minute, do some multiplication and some cleaning things up. And then we'll jot them back together and make sure that we all have the same thing. Okay, what do we get for the cross product? Most of you seem to be done writing.
T 1/2 t squared and 1.
Okay, that's what I have as well. Is that okay? All right. All right, so one of the things that we talked about in Calc 1, when we're looking at derivatives, is whether or not things are smooth in graphs, right? And in particular, when we have graphs that are smooth, that's when we have derivatives, and when graphs aren't smooth, we have places where our derivatives don't exist. So we're going to take a look at the idea of being smooth with vector-valued functions. All right, so we say a curve traced out by the vector-valued function r of t is f of t, I defined as f of t, g of t, h of t, is smooth on an interval I if r prime, we'll just say r prime, is continuous on I, and r prime of t does not equal 0, except possibly at the endpoints of I. So determining if something is going to be smooth has two conditions. The condition is that, oops, that was supposed to be a highlighter. The condition is that r prime of t is continuous and that r prime of t does not equal 0. So we're going to use those features and look at example 3 to decide when a graph is smooth. To determine if the given curve r of t is smooth. All right, and our r of t is, we're going to do just a planar curve, t to the 4th minus 2t squared and t squared minus 2t. So notice that the definition all is hinging upon r prime, not on r itself. So I need to take the derivatives and then assess whether they match the criterion. So r prime of t is what? Four t cubed, then what? Minus 4t. The other one is 2t minus 2. Okay, so number 1, if you will, is it continuous? Yeah, r prime is continuous. And you might be thinking, well, I mean, I know it is, but like, how can I justify it? Early on in our book, they proved that all polynomials are continuous. You don't have any problems with that, and that their domain is all real numbers. It's got a lot of beautiful things about polynomials. So the reason this is continuous really is because the components f prime of t and g prime of t here are polynomials. There's similar statements for radicals and rational numbers, rational functions as well. As long as you're on the domain for them and you don't have a domain issue, then they're smooth too. So you get all those for free, basically, from the earlier chapters in this particular book and Calculus 1 in general. Our second piece is to determine if they are not 0, right? So we want to figure out if r prime of t is equal to 0 anywhere. So we want to, in particular, take a look and see if we get the 0 vector, right? So we want to look to see if 4t cubed minus 4t is equal to 0 at the same time when 2t minus 2 would equal 0. They are going to equal 0. The question is whether or not they do it at the same time, because that would give us our vector being 0. Now, the second function actually is easier to solve, right? 2t minus 2 equals 0. So if I solve this, and what is t? 1. And so if I put the number 1 into the other function, will it also equal 0 at t equal 1? It does. And you don't necessarily have to factor it to show that, although you certainly could if you wished, right? This would be 4t squared and, 4t and t squared minus 1, which would give you locations of t being 0 at 0, the function being 0 at t equals 0 and at plus or minus 1. So you can do it that way, or you could actually just show that at the t equal 1 location that we've got a problem, and nowhere else could we, because nowhere else is the g of t function equal to 0. So when we're writing our issue about being smooth on this, this one is smooth, so it's just not smooth at that one location. So hence r of t is smooth. Keep wanting to put an E on the end. Smooth for all t in the interval I, except for 1. So that's the only problem spot we have. Notice if we had a continuity issue with the original piece, we would also have a break in where it's continuous there too. That would happen as well, or not continuous, but smooth. So if there's a continuity issue, it can't be smooth there. Okay, let's take a look at another definition. We talked about derivatives, so where would we go next? Integration. So for the vector valued function, R of t equals f of t, g of t, h of t, we define the indefinite integral of R of t on AB as our integral of R of t dt is the integral, by definition, of the f of t, g of t, h of t, dt, but really that's just the integral of each of those individual functions of t, right? So the integral of f of t dt, the integral of g of t dt, and the integral of h of t dt. Or more compactly, you could even go to another notation that you're familiar with where we change these to capital letters. F of t, g of t, these are supposed to be t's, and I'm making them x's. Let's make them t's. F of t, g of t, and h of t. Everything's just like what you expect it to be, right? It's very nice. Huh? For once. Yeah, for once. Okay, so let's actually do an example of an indefinite integral. So we're going to find the indefinite integral. And we're going to do this one. So the integral of 2t minus 1 I plus 4t cubed j plus 3 square root t k dt. We used lowercase r, so now we'll call this capital R. All right, so what would we do? Or what would we get even? Do you want to, we'll write an IJK format since it started out that way. How about 2t minus 1? What does that give us if I take an antiderivative? T squared minus t. I'm missing something. Plus c. So if you're going to use plus c here, we do need to be, which you're going to, c or k or whatever. You need to identify C1 because we're going to have a C component on all three of them, and they wouldn't necessarily need to be the same thing. So plus C1, and then it's all of this is times I. How about the next one, 4t cubed? T to the fourth plus C2, J. And then square root of t's are kind of messy, but they're not too bad. You all are good with it, right? T to the 1/2, right? So what would we have? T to the 3/2, and then times 2/3, right? Or divided by 3/2, yeah. And then if we change it back into that radical notation, it would be 2, and then we'd have the square root of t cubed. That'd be one way to write it over 3.
Times 3.
Times 3. At the beginning of it, I missed that part. Thank you. Yes, there's a 3 right there. Yes, you're right. So we'll take one step to clean that up, and then we have our plus C3 here, right? And then K. So on this one, the 3's will cancel, and we'd have that. So t squared minus t plus C1 I plus t to the 4th plus C2 J plus 2, and you could do 2t square root of t if you wish, or 2 square root of t cubed plus c3. Okay. And I didn't actually give you the next definition, but I have a feeling you're going to know exactly what to do when I give you the problem, because I don't think it really needs an additional definition beyond what we've already established, because we're going to look at a definite integral. So we're going to evaluate the integral from 0 to pi halves of, and this is arbitrarily written as a cosine t I plus a sine t j, and then plus k dt. So it's going to work just like you expect, right? We're going to do the indefinite integral like we did before. We aren't going to need any of the plus c's. And then we're going to evaluate this at an upper limit of pi halves and a lower limit of 0. So what's the antiderivatives first? So antiderivative of a cosine t.
Sine t.
A sine t. And again, we don't need the plus c's, so this would be I. How about the antiderivative of a sine t? Negative a cosine t, j. And then the antiderivative of k. T. So tk. So it's not really antiderivative of k, but antiderivative of 1. So tk. And we're evaluating at pi halves down to 0. So when I evaluate this at pi halves, it's going to be component-wise. I'll just do it component-wise. So this is a times the sine of pi halves minus a times the sine of 0 times I plus a cosine of pi halves minus a cosine of 0 j plus, and then I have pi halves minus 0.
To be
Did I miss one?
negative a cosine pi over 2 minus.
Yes, I was meaning to leave that a negative out here. That's what I meant to do. So let me put that negative out there. You can distribute it through if you wish. Yeah, and we will soon. All right, so what is the sine of pi halves? Do y'all remember?
0.
Nope,
1.
that one's 1. So sine of pi halves is 1. What's the sine of 0? That one's 0. How about the cosine of pi halves?
0.
That one's 0. And the cosine of 0? 1. Whoops, 1. So using that piece, those pieces of information, the first one I end up getting is a minus 0, or just a, right? That's really not a great hat. Let's try that again. Okay. The second one, I have 0 minus a, but then I have a negative a in front, so I have positive a, j. And then I just have my pi halves k. I have one last example. We're going to finish up right at time. Number 6. I think there's space here. We'll try. We're going to find R of t with the following initial conditions. So the R of t, the R prime of t value that we are given is 4e to the 2t I plus 3e to the t j. And we're going to do a planar curve. So it's, and then R of 0, we're told is 2i. So we're going to take our antiderivative. I have changed my mind. I want more space. Okay, what is the antiderivative then of the 4e to the 2t I? What's just the derivative of e to the t? Sorry, the antiderivative of e to the t. It's e to the t. And the coefficient on the t of this one, the 2, means that it's going to be a division factor instead of being a multiplication factor, which is what we get if we were doing a derivative. So while we have a 4e to the 2t, it will end up being divided by 2, right? Okay, so this is this plus c1, and all of that is I. And then how about the antiderivative of the 3e to the t? That one doesn't change, so it's 3e to the t plus c2j. Now the kicker here is that this is supposed to, if I evaluate it at 0, equal just the 2 component on I, 2 in the I component. So if I put in r prime of 0, or put in 0 for t, this would give me 4e to the 0 over 2. This simplifies to 2, of course. I should have just done that. So that's a 2. So 2e to the 0 plus c1. And then I have 3e to the 0 plus c2. What's anything to the 0 power? 1. So these are giving us just 2 plus c1 and 3 plus c2. And it's supposed to be that the I component is 2. And that would mean that my j component is 0. So what would c1 have to equal? 0. And what would c2 have to equal? -3. And so we take our r of t that we had previously found as an arbitrary r of t, and we put back in the c1 and the c2. So we have 2e to the 2t, and it's plus 0, so that's just it, and then it's I. And then we have 3e to the t minus 3j. Is that all right? Okay, let me write in the homework for us, and we'll be finishing up for today. This is page 834. It's 10, 12, 14, 21, 22, 24, 25, 31, 33, 41, 45, 48, 51, almost done, 54, and 57.